last week we looked at drawing graphs, drawing cubics from the equation. So we will learn that if we had an equation that looked something like this, but with numbers where A, alpha, beta and gamma are, we could draw the intercepts of the graph and make an attempt at sketching it. Okay? Now today, largely, we'll be looking at, given a graph or given the roots, how do we find the equation of the cubic? So similarly, when we did quadratics, first of all we started looking at how to sketch a quadratic, and then we looked at how to find a quadratic formula given the graph. Today we'll be looking at how to find the cubic formula given the graph or given a piece of information about the graph. Now, first form we look at is simply the linear intercept form. Essentially, our cubic equation is to split up into three linear sections. So, here, here, and here. Each of those linear sections corresponds with an x-intercept. So, for example, when x is equal to alpha, we have a 0, or a root, or an x-intercept. When x is equal to beta, and when x is equal to gamma, each of those three produce a root. So we can say that this cubic cuts the x-axis at three distinct points. And A is what generalizes it. So that will make it either like this or like this. Yep. And we'll decide how split out or narrow it is. So if we were asked to find all cubics with roots 2, 3, and -4, how should we go about that? Leave the A, good. We have y equals A bracket x take 2, x take 3, and x plus 4, with A not equal to 0. So each of these numbers corresponds with a linear root. And that gives us all cubics with those three intercepts, or those three x-intercepts. That's alright? Sweet. Now, once again, I apologise for my graphing. I really do struggle to draw on this thing. But the important information is there. Find the equation of the cubic below. Now, when we did quadratics, and we were given two roots, we used that two linears model of a quadratic with an A out the front. Here we have three roots, and then go.
I think I thought that the cubics have a slope of 0 or something.
Only when you have something like when you have an x to the 3 term, like on its own, or if you do x to the 3 plus 4, that moves the point of inflection, or the stationary point of inflection you're looking at here. So on this graph, there is still a point of inflection. It's where the graph goes from concave to convex, so it'll be about there. Given my drawing, there could be several points of inflection, but on the cubic, there's guaranteed to be one, okay? Now, if we were going to find the equation of this cubic, we take the form above, because we have the three distinct roots. So y equals A, x take alpha, x take beta, and x take gamma. And then we substitute in the roots. So we know that we have, with A not equal to 0. Wow, where did I go there? Sorry. Leave the A out the front. X plus 2, x take 1, and x take 5. So those three linear factors correspond with these three zeros, or roots. Now, same with quadratics, we substituted the roots in to find the terms in the brackets, and then we use the final piece of information to find A. So with quadratics, we use that point to find A, and the same with cubics. So if we want to find the exact equation of cubic, we should be able to define A also. So here we substituted the point 0, 3. So when y equals 3, x equals 0, A bracket 2, neg 1, neg 5, A equals, 3 equals 10A. It's gone too quickly. A equals 10 on 3, 3 on 10. Okay. So our entire quadratic formula is 3 over 10 bracket x plus 2, x take 1, x take 5. Now if they've asked for it in the general formula of ax cubed plus bx squared, etc., you'll then have to expand the brackets out. Okay? But I'm not going to go through that now, we're short of time. Once again, a gorgeous graph. Majestic even, yes, thank you. The important point is that it touches there. So when we had something touching with a quadratic, so it came around and touched a point, it would be called a repeated root. Here, same thing happens. It's repeated. So starting from the formula we had above of y equals ax take alpha, x take beta, x take gamma, we can say that this root here of 2 is repeated. It occurs twice because it's touching. So we have y equals a bracket x plus 1. That gets us our first root. And then x take 2, x take 2. It happens twice. And that assures we still get the cubic. Now this simplifies to y equals a bracket x plus 1 bracket x take 2 all squared. Now those of you who looked at your folios will start recognizing some of these sorts of equations as they pop up in the folios. Right. Now we haven't found all the information about this yet. What else do we still need to find? Alright, any hints on how to find A? Substitute, again, always substituting. 3 equals A lots of 1 lots of minus 2 squared. 3 equals 4A. A equals 3 on 4. Giving us a final equation of y equals 3 on 4 x plus 1 x take 2 all squared. And if they've specified the form they wanted in, then you'll need to expand. But otherwise, that's fine. Alright? So, using this form here, the 3 linear forms, is quite easy. When you've been fortunate enough to be given 3 linear intercepts. 3 intercepts you can easily identify. However, it doesn't always work out that nicely. What happens much more often is you get a cubic in the form of a linear multiplied by a quadratic. So we saw a special case of that above. Here we have a linear multiplied by a quadratic. So that works out nicely for us. However, quadratics, as we know, have a whole series of properties. So when we have a cubic in this form, a linear and a quadratic, we'll always have one real root, because linears always give a real root. And a quadratic will again determine on its discriminant, will depend on its discriminant. Now the reason this has those 3 solutions, or the nature of those solutions, is because of the null factor law. Who remembers that one? More or less? To jog your memory, if you have AB equals 0, then either A must equal 0 or B must equal 0. I can say or and B must equal 0. So if we're looking for roots of this, of where a linear is equal to 0, so we have a lin and a quad, when we set y equal to 0 to search for the x-intercepts, we can say that either the linear is 0 or the quadratic is 0. Okay. Now the linear is 0 is easy, because finding the 0 of a linear term is pretty basic, because they look like that. Or it might look like 3x plus 2, or 5x take 1. But either way, you can find when, for what values of x that's equal to 0. However, the quadratic, we know, has different solutions for when it can equal 0. A quadratic can equal 0 when the discriminant is positive. It has 2 distinct real values that for which the quadratic is equal to 0. Use my words carefully. When the discriminant is 0, then there is only one repeated real value for which the quadratic is equal to 0. And if you worked out the discriminant of that expansion, you'd find out that the discriminant was 0 for that. And finally, if the discriminant is less than 0, then the quadratic is equal to 0 for two distinct imaginary numbers. Okay? So, those of you who got the quadratics will get the cubics because the same principles apply. So, if we're asked to find the zeros of this algebraically, I should say that, algebraically. Language, Corey. Whoever watches this on YouTube will hear that loud and clear. I can't spell algebraically. And I can't delete it either. Alright, keyboard's broken. It's staying there. Alright, while I figure out how to use my technology, can you guys start attacking that? Finding its roots algebraically. One can be done by inspection, just simply looking at it, but the other two will be more difficult to find. So who can see the one root? It's easy. X equals minus 1. So that is one value of x for which the whole thing is equal to 0. But we need to find values of x for which the second part is also equal to 0. We'll work it out. No. It's finally working. Alrighty, so what do people try? Thank you. So our first one is x equal minus 1. That one everyone got straight away. What about the quadratic? What roots came out of the quadratic? Two imaginary numbers?
Yes.
Which you found using quadratic formula, right?
Yes.
And they were x equals minus 1 plus or minus 3i. So we can say that the roots, or zeros, are equal to minus 1 plus 3i and minus 1 minus 3i. No, you're right. Minus 1 plus or minus 3i will get you both of them. Alright. Now, other challenge. Find all cubic polynomials with zeros 3, 2 plus or minus 3i. Now, this builds on the quadratics. So we remember that R cubic can be written as a linear and a quad. Sorry. Cool. Yeah, quadratic.
we know that that term there will be for the linear, and those two will be for the quadratic. So we can say that our linear straight away is x take 3, and we want all cubic polynomials, so there's an a out the front. However, now we need to find what quadratic produces roots of 2 plus or minus 3i. And this is exactly the same as the test question, yes? You don't remember the test question? Alright. Couple of ways to do the test question. The slightly longer way would be to remember that...
Is Alicia... Sorry.
You right?
Experience stuff.
Who's the other person's going to win this? Are you seeing her?
Yeah,
Can you give her one of those as well? Yeah. Get her as soon as possible. Okay.
just need photocopies of you.
Alright, so who remembers this way here?
Oh,
If we're, yes, that, and then because that's giving us a quadratic with roots 2 plus or minus 3i, or we can use the sum and product of roots. Either way works. Sum and product is quicker, so I'm going to use that here. The sum of the roots, so alpha plus beta, is going to equal to 4, because that's come from 2 plus 3i plus 2 take 3i. Sum of the roots is 4. Product of the roots is going to be 4 plus 9, 13. 13? Negative 4. I've got it right, yeah. That's fine, good. And everyone happy with how I got 13? So that'll be this 2 plus 3i multiplied by 2 take 3i, which will come out to 2 squared, 4 minus 9i squared, which gets you your plus. So 4 plus 9 is the 13. Now, given this, or if you like this way above, where am I going? If you like this way above, you'd expand that out. But if you expanded that out, or use your sum and product rule, eventually you'd end up here, where you have x squared minus 4x plus 13. Okay? Now that is certainly worth practicing, because that expansion people can make errors with, and this one here people forget to change the sign in front of the sum. Alright? So if we're looking for all cubic polynomials with zeros 3 and 2 plus or minus 3i, we get a linear factor of x take 3, and then we get a quadratic that produces zeros of 2 plus or minus 3i. And of course I've forgotten that a is not equal to 0. Yes. Because we need the a out front because we want all cubic polynomials. Alright. Half a mark every time. And some people suffered from that, I think. Alright, so now we know how to find zeros of a cubic given that form. And we know how to find a cubic given 3 zeros. Okay? Now, slight step away from that, because we'll need it for the final little section of this, is polynomial equality. Essentially, this is similar to equality of imaginary numbers, where we had, if we had 2 plus 3i equals a plus bi, then we could say that 2 is equal to a and b is equal to 3. Same thing happens with polynomials, but it's called equating coefficients. So you take the coefficient of x cubed on one side of the equation, that is equal to the coefficient of x cubed on the other side. So a is equal to alpha, b is equal to beta, c is equal to gamma, d is equal to theta. Alright, so the coefficients line up. and equate. Just like here, the real part equates with the imaginary, or with irrational and rational. Those parts equate. Same here, the coefficients equate. Sorry for the mess of Arabic and Greek letters. Or Arabic origin and Greek letters.
Yeah.
We have to teach literacy. I'm on the literacy bit. So, how do we use this property to find A, B, and C? Yes, we expand. However, before we expand, we can save ourselves a little bit of pain. So, how could we get a constant term out of the expansion? What are the only two that multiply together to get us a constant term? 1 times C. So what is C? 2. Lovely. We don't have to expand with all of C. That becomes 2. Similarly, what will get us an x cubed? There will only be 1 x cubed in that expansion. A is 2 as well. Alright? So before you do the expansion, try to snipe off a couple of the easy ones. Yeah? Just pick them off. Did I just write C equals C? Yep.
The only one you really need to do is the A
Good. So you can jump in.
the BX.
Alright, so rather than doing the entire expansion, Alicia's pointed out, actually, you can just... Alicia... Blame Miss Rogers. Alicia has pointed out that you can just pick on one. So let's say we want to get x squared. What expansions... Did that not come up? Oh. What expansion pairs will get us an x squared? You'll have this one and that one. Yeah? Are there any other pairs that will produce an x squared term? No. So we can say that x times bx, so bx squared plus this term here, 2x squared, is going to be equal to this one here, x squared. So instead of doing the entire expansion, no, there, positive. My circle went through it, sorry, it is a positive. Okay, now we can divide through by our common factor of x squared to have b plus 2 equals 1. Therefore, b equals minus 1. Now, what would have happened if Alicia had chosen not the x squared term, but just the x term? So we still know that a is 2 and c is 2. But what if we were concentrating on this here? What expansions would get us a single power of x? Good. So there would be a cx, which is 2x. Yeah? Because this one, so this expansion here is 2x. And the other one would be bx. And that is all equal to minus 5. What's gone wrong here? Done something wrong. Huh? Done not good. Which can't?
Why was AX squared 2?
Which one?
AX squared. The first one.
Because if you to get an x cubed, you have to do x multiplied by ax squared. So a is 2. 1 multiplied by 2. A is 2. 2. What's the you see the problem?
Yeah.
But where did we go wrong?
Is it the question?
No, it shouldn't be. Because I copied it directly out of the review set.
Maybe the wrong.
No, this should work for all values ABC.
Well, you've already done A, B, and C. That's what you did.
No, we've just found A and C. Oh, you mean for B? I'm just checking B. Because we should be able to find B using the x squared terms. And we should be able to find B using just the simple x term. And they should be the same. Just checking this then. X on x squared gives you 2x squared. 2x squared. 1.
It's the question.
The question?
It's x take 1. In the review set, it's x take.
Which one? There.
No, in the review set, it's x take 1, ax squared plus bx plus c equals 2x cubed plus x plus 2. So it's the question.
My apologies, I copied this down late last night. Huh? I lost huge amounts of marks. Alright, so copying mistakes are horrible. From the top then, how do we get A and C? Huh? Good. So C is minus 2. A is 2. Yeah? Now try for B. So we can say that using the x squared term, eventually we're going to end up equals with x squared. We have A times bx and minus 1 lot of that. Bx squared minus 2x squared equals that. B equals 3. Because the x squareds go, and then the minus 2 goes over to become a plus. And now we can try the same using the single term of x. And we get the single term of x by doing 1 lot of bx, minus 1 lot of bx, and c lots of x. That's better. Alright. So my apologies with this one, but the important thing to remember is to equate coefficients, try and pick off the A and the C first, and then choose either the x squared or the x term to find the B. Last little bit. Now, if you can get this is where the whole lesson has been building up to this. Find the exact zeros of this. Now, write it down, and then we will do it in a sec. Alright. So, if we look at this, we can't immediately start to factorize it or even really guess at what the zeros are. But we do know that it can be split like this. We can split it into a linear and into a quadratic. Okay? So we know that one of the roots should be quite simple. We know that the linear should be easy enough. And we can find that linear by graphing. That's the graph. Do some zooming to change it. And then looking at the intercepts. So if we hit gsolve root, now that number isn't particularly pretty, is it? We couldn't put in x plus 3.64557 whatever and really hope that that's a linear factor. So we look at the next one. That's better, isn't it? That's ugly. So that's the one that we're going to use for our linear. Now what linear factor would result in a root of 0.75? 4x take 3 would do it nicely. So you can say that this linear factor is 4x take 3. Now if you aren't comfortable that that produces an x of 0, you can simply say that the linear factor is x take 0.75. Okay? Both ways will work. And I think x take 0.75 is perhaps more intuitive looking at this. Because the root is 0.75, so the linear factor associated with it is x take 0.75. Either way works. Now, we know that the rest can be split up into a quadratic. Yeah? So we can write the general form of quadratic here. ax squared plus bx plus c. And we know that that entire thing equals 4x cubed plus 5x take 30x plus 18. Can anyone see where this is going? Yes? Alright, so for those who can't see where it's going, I'll spell it out a little bit for you. We know that a linear, a cubic, can be split into a linear and quadratic. We've got the linear factor. We can equate coefficients to find a, b, and c. Once we've got the quadratic, we can use the quadratic formula to find the exact roots of that. So it's like this question combines this one. So we've got a linear and a general quadratic equals a cubic with this one here, where we have a linear and a quadratic, and we need to find all three roots. Alright? So this last sort of question is a beautiful one to come up in tests because you know there'll be tons of marks associated with it. Because you'll need to find the linear factor, write out a quadratic, equate coefficients to find the quadratic, then use a method to solve the quadratic to find exact solutions for that quadratic. Let's go through it. Alright, so equating coefficients, which two can we snipe off straight away? C and A. So what is C? Good, because 3 times C is equal to 18, so therefore C must be minus 6. Gone. A, beautiful. A is 1. Now that would be slightly different if you had 0.75, but the whole thing would work out in the end. Alright, now, which one should we choose to go for B? The squared term? I've forgotten to put a squared there. Alright, so we get squares by doing that times that, and that times that. So 4bx squared minus 3x squared is going to be equal to 5x squared. The x squareds go, leaving us with 4b minus 3 equals 5. 4b equals 8, b equals 2. Love it when that happens. So now our quadratic is, or rather our entire cubic is 0 equals 4x take 3 bracket x squared plus 2x take 6. Alright, now remember we were asked for the exact zeros. We can find the exact zeros of the linear, that's easy. We need the exact zeros of that. No, because negative 4 times positive 2 gets negative 8. Quadratic formula? Sure. X equals minus b plus or minus the square root of b squared take 4ac over 2a minus 2 plus or minus the square root of 4 minus 4 dot 1 dot negative 6 over 2. Square root of 30? No, 28 over 2 equals minus 1 plus or minus, take out 4 to root 7. Okay, that's quite a simplification. What I've done is taken the root 28 and made that equal to root 4 times root 7, which is equal to 2 root 7, and since it was all over 2 they go, leaving us with just the 7. And the minus 2 here was over 2, so it goes and becomes minus 1. Okay? So now our three roots are x equals 0.75 and then minus 1 plus or minus root 7. Now how do we check this? Well, we check this by putting into our calculator 1 plus root 7, and 1 plus root 7 is 3.6457. So we go back to our graph and we'll ask which the points are. Huh? Yeah, I just did that to get the negative 3.64. Alright, so we're running out of time, so I'll talk that through quickly once more from the top. To find the exact zeros of any cubic, you graph it. From the graph, you should get one easy one. Write the easy one to one side. What's left is a quadratic. Equate your coefficients to find what that quadratic is. Once you've found the quadratic, use quadratic formula to solve where the two roots of that come from. That will give you your two roots that might be complex, might be imaginary, might be real, and your one real one from there, which gets you all three. That is quite a lot. That work there is for the rest of this week. Enjoy. And that's practice on everything we've done today. And I know it may have seemed like a blur today, but when you're practicing going through step by step, it builds up to that final problem. Cool. Sorry about copying the